Everybody, there we go. We were actually doing a little test right
Live
now.
stream on now.
Very good. Well, good evening, everybody. My name is Bert Dicht. I am the Managing Director of Membership for the National Space Society. And on behalf of my colleague, Larry Ahern, Vice President of Chapters, I'd like to welcome you to our Space Forum this evening. Tonight, we're going to be talking about scaling new heights, delivering power to the space elevator climbers. And we are looking for a really fun session. I do need to do one thing with the chat. If you hold on a second, everybody. I just want to make sure everyone can access the chat. Yep, very good. Oops. So again, welcome to the Space Forum. And as always, I want to just share our agenda here. Okay, sorry, got a little trouble with the slide advance there. But we'll be going through some virtual etiquette. I have a few NSS announcements to share. Then I'll be talking about what's coming up next, and then we'll get right into our program. So as always with our virtual etiquette, if you have a question and like to submit it, please use the Q&A function. It's the best approach because it's seen by our speaker directly, and it's easier to pick out the questions from there. But you are absolutely welcome to use the chat function as well, because everyone can see it. Be respectful of both our speaker and the audience. We'll do our best to get to as many questions as possible. We did get a number of questions, as always, that were submitted, and I know our speaker is going to try to address some of them in the presentation. So hopefully we're looking forward to that. In terms of our announcements, I'd like to remind everybody to please give to our cause. If you're enjoying programming like this, the Space Forums, the town halls, we ask you to donate to support the National Space Society. I want to thank everyone who's donated in the past, and thank you in advance for any donations that come our way. We really do appreciate it, and I will put this into the chat, the link, so you have it. Also, at the end, feel free to complete our Space Forum survey. It only takes a couple of minutes to do. It's very easy to do it. It's anonymous, completely anonymous, and your feedback will certainly help with our planning future events. So thank you in advance for that as well. I would like to put one announcement out there for everybody. We have something really big coming up. This is the Space Settlement Summit. The Space Settlement Summit is a workshop we do every year now. The idea is to bring together the key individuals who can make things happen when it comes to space settlement. And this is a really interactive type of event. It's not just people talking to you. You're going to be going into breakout rooms and coming up with ideas and plans to help move space settlement forward. The topic this year is the geopolitics and policy of space settlement. You can get a look at some of the great speakers that we have attending, and there's a lot more. It's a great action-packed, fun 2 days. And as I said, it will be highly interactive. So I encourage you to consider it. It's going to be November 8th and 9th at the Center for Space Education here at the Kennedy Space Center. So you'll also be able to get a chance to see our NSS office as well. You can go to spacesettlementsummit.nss.org to get more information. And because you're here on the Space Forum tonight, you can use promo code SSS100 to save $100 off regular and senior registration. And you can also use SSS-student-special for $100 off student registration. Or please feel free to reach out to me as well. I'll be glad to answer any questions. It's just coming up really fast. I've been to the last two, and I can tell you they were really great, really informative. And it's a lot of fun to be part of the solutions. It's not just, again, listening to individuals. So I encourage you to come and see us here at the Space Settlement Summit in a few weeks. So what's coming up with our Space Forums? Well, this is the first one we've done in a while. We were supposed to have a Space Forum last week, but because of the hurricane that hit here on the Space Coast, Hurricane Milton, both myself and our speaker were impacted. We didn't know whether we'd have power. and it just felt like we should not run a space forum that day. So we never even announced it. We've actually just rescheduled it now for next week. So Josh Zugan from Via Space will be here to talk about what they are doing. They're a startup rocket company here on the Space Coast, and I think you'll find that very interesting. I've got a couple other things coming up for you. November 14th is going to be it's a new book, The People's Spaceship, NASA, the Shuttle Era, and Public Engagement After Apollo. This book was written by Amy Page Kaminsky. It's a really fascinating different look at the politics and issues behind the development of the space shuttle. Amy is a former NASA employee, and I think you'll find the presentation really interesting. And we'll be giving away four copies of her book as a virtual door prize as well. Then the week after that, November 21st, we have another new book called Re-Entry, SpaceX, Elon Musk, and the reusable rockets that launched the second space age. And Eric Berger wrote this. He also wrote an initial book about SpaceX called Liftoff, which is very interesting. And with the great recent success of SpaceX, I think you'll find this also fascinating. And we will be giving away 4 books as well as a virtual door prize for that too. Then the last Space Forum of the year is going to be on the 5th of December. It's our annual 2020. It's our annual Space Year in Review with Larry Boyle. So I know you're going to enjoy it as well. We lining up a number of speakers in 2025. I do have a confirmation from Trey Carlson, who is the Chief of Staff at the Kennedy Space Center. He is going to do a really interesting presentation on the development of KSC and Cape Canaveral Space Force stations as commercial spaceports. It's a really great presentation. Haven't lined up the final date yet, but it will be in January, and we've got a number of other things that are in the pipeline. So hopefully I'll have a lot more to share with you when we do next week, or certainly by the 14th of November, we'll have all those dates lined up. So hopefully you can join us. We've got some good sessions coming up for the end of the year. So now it's my pleasure to introduce our guest speaker for the evening. And Larry Bartoszek is a friend of mine and also an NSS member and an NSS Space Ambassador. He has been a presenter at the ISDC. Last year, he helped us out and was part of our speed mentoring session at the ISDC for the SED students. And I think you're going to enjoy his presentation. He has a dual degree in mechanical engineering and physics from the University of Illinois. He's a licensed professional engineer. He's a member of the American Society of Mechanical Engineers, like me, member of the American Welding Society, ASM International, the Chicago Society for Space Studies, and of course NSS. And as I mentioned, he is vice president of the International Space Elevator Consortium. So you're getting a really knowledgeable individual who'll be talking tonight. Also want to mention Larry is the owner of Bartoszek Engineering. It's a consulting firm that specializes in mechanical design for nuclear and high energy physics research. And these works worldwide. So I think you're in for a treat. I'm going to now turn this over to Larry, so I'm going to stop sharing. And Larry, thank you for joining us. We're looking forward to the presentation.
Thank you for having me. All right. I've got a lot of material to cover tonight. I'll try not to go too fast. Just yell out in the chat or whatever if something is not going well.
We'll do that, Larry.
What's that?
We'll do. Absolutely.
Okay.
Yep.
I want to give a shout out to the president of ISEC, Dennis Wright, our new secretary, Martin Lades, and one of the members of our power study team, Avery Davis. They have all contributed to this talk. We are currently in a study for all of 2024 and probably a good part of 2025 to determine how we send up power to the climber. And I'm going to discuss 2 options. There are 2 primary options to power a climber on the space elevator over its whole trip. One way would be wireless, using lasers, microwaves, or solar power. The other way is wired, assuming that the graphene material that the tether of the space elevator is made out of can be conductive enough. It's 6 times better a conductor than copper. There are a couple of possible options to get out of the atmosphere by some very clever ideas, but they don't drive the whole way. There is also a very interesting option that was just recently brought to my attention, using longitudinal mechanical waves in the tether, but that is problematic for the dynamics of the entire tether system. It's a way to transfer power. It's also a way to destroy your space elevator if bad things happen. So the first thing we need to talk about is the requirement. Before we can design the power system for the climber, we have to understand how much power is needed to put a kilogram in geo. And the way you calculate that for the space elevator, you don't have to add the kinetic energy of satellites in orbit. The reason for that is because that energy comes from the tether. What you do have to do is look at the potential energy change from the surface of the Earth to geo, and the answer is it takes 53.1 megajoules of energy for every kilogram to boost objects up the tether to geo. If you were 100% efficient, that would be the minimum and all the energy that you would need to put a kilogram of mass at geo. And if we assume a 20-ton climber, that's 20,000 kilograms of material. A 20-ton climber requires a terajoule of energy. And if the trip takes 8 days, which is 691,000 seconds, then the average power required over the trip is a little over 1.5 megawatts. Now, the issue is you don't get to distribute it evenly over the entire trip. This is a graph of the acceleration due to gravity and how it drops off as a 1 over r squared function. So the climber weighs its full weight at the surface of the Earth at an altitude of 0. And at an altitude of 2,500, almost 2,600 kilometers up, the climber only weighs half as much. Now, 2,600 kilometers up is higher than low Earth orbit. So the climber has been climbing for a couple of days at this point, but the total amount of power required to make it continue keeps dropping off, and it drops off fairly rapidly. At 6,200 kilometers up, the climber only weighs a quarter of what it weighed on the pad. Now here's a graph of the power required, and I'll show you where this comes from. For a long time, we've argued that you could limit the total power delivered to the climber to 4 megawatts. If you do that, the climber can't climb at its maximum speed until about 4,000 kilometers up. And I'd like to make it a little faster. So I would like to open up the possibility of delivering more power. And I'd like my power system to be able to deliver as much as 11 megawatts of power on the pad. Now, there was a famous book. As a matter of fact, I keep it by my side all the time. Edwards and Westling's book, The Space Elevator. Brad Edwards did the first practical design of a space elevator back in 2003-ish on a NIAC grant. And what did he propose? He proposed using a free electron laser that was being planned at the time to deliver 2.5 megawatts of laser power to a 20-ton climber at geosynchronous orbit. And he was talking about, he was talking about 59% conversion efficiency for the photocells. That's probably higher than we can reach. He was also talking about 540 kilowatts per square meter power density. That's really high. But we'll talk about where some of these numbers come from. He was talking about photovoltaic arrays on the receivers on the construction climbers starting at 4 meters in diameter and go up to 10 meters in diameter as climbers got larger. And the transmitting laser would have a 12-meter diameter aperture with adaptive optics to point the beam on the climber's receiving array. So back in 2023, I did a conceptual design for what a 20-ton climber would look like. This climber is holding two cryostats full of liquid oxygen. The idea was our customer was going to be Elon Musk, who needed a lot of liquid oxygen and fuel. And he needs it. His original plan is to do it at low Earth orbit, but it's very easy for the space elevator to create a fuel and LOX depot at GEO. So that's where I was planning on delivering these LOX tanks. And this is the tether, the tether that starts at the surface of the Earth and goes up to GEO. And this is the 20-ton climber that has 10 megawatt scale motors rolling these wheels that are pressed up against each other up the tether. And this is the relative size of a 5-meter diameter array. This 2.76-meter diameter array was an idea that I had that I think will never come to fruition, and that's for a photovoltaic array that can handle 1 megawatt per square meter. I don't know when that's going to happen. But here's a 10-meter diameter array. And one of the things that's missing from this conceptual design is, how do you hold up these arrays? That's something I'm hoping to get to shortly, doing some mechanical design of the arms that hold up these arrays, especially against gravity, because everything on the space elevator feels the effect of gravity. It's not like you're in low Earth orbit in microgravity. You are not in microgravity until the end of the trip over a week later in geosynchronous orbit. So these also act like sails to the wind. So I need to look at drag forces in the wind. And this blue shell is a concept for the amount of area that I need as a space radiator to dump the waste heat off the climber. And that turns out to be kind of a big deal. That's a whole nother talk, the thermodynamics of the climber. Now, the motor characteristics, that conceptual design of the motor was originally derived from a motor developed for electric aircraft by the Magnix Corporation. So it's a Magni 650. What I discovered when I used their motor as their catalog calls it out, it was unable to lift the climber. Basically, when you design all the subsystems in and you calculate the total mass of the climber and you compare it against the torque output of this motor, the motor can't lift itself. So I made a conceptual leap and I said, we will imagine that there is a motor that is twice as capable as this electric motor. And I have solid physical reasons for believing that you can build a motor with this kind of power. But so this would be the torque output of that motor, 5,600 Newton meters. And at its rated speed and torque, it would be using 1.12 megawatts. And since there's 10 motors per climber, that's where I came up with the number of 11 megawatts of total electrical power at the full torque and rated speed, which would happen relatively close to the surface of the Earth. These motors, I'm imagining, are operating at 800 volts, the same voltage that a Tesla operates on. And I've tried to use Tesla battery technology as the buffer. The climber does need a battery in case of interruptions in power. But what you know is if you're delivering this much power at 800 volts, you're taking 1.4 kiloamps of current. And since there's 5 motors on each half climber, the bus is carrying 7 kiloamps of current. This is a significant amount of current. So let's start by talking about lasers. And then something important comes out of the laser system design that is very relevant to the microwave power possibility. I took a 3-prong approach to laser design. First, I wanted to look, now I know how much power I need. So the question is, how many losses are there in delivering power to the climber? Because the ultimate goal of this study is to determine how much power do I need on the ground to give the climber enough power to make the trip up to GEO. And what I know is the atmosphere does terrible things to laser beams. Okay, it's only 0.3% of the range of the trip, but bad things happen to light that goes through the atmosphere. But the thing about this part of the study, the transmittance and the diffraction limit study, tells you the laser wavelength light that works best. and gets out of the atmosphere. And then the next question is, what laser technology can make that color light? And then the third question is, what kind of photovoltaic receiver can convert that light most efficiently back to electricity so the climbers can be driven on electricity? So here's a very informative chart that I got from the Wikipedia. There are two windows for light coming in or out or away from the Earth. The visible window, where a lot of the power of sunlight gets through the atmosphere, is in this wavelength range, and it's right in the visible light range. This orange line is at 0.5 microns, which is green light. So blue light goes off to the left and red light goes off to the right. And then you start getting into the infrared radiation. And there are windows in infrared that can also transmit light out of the atmosphere. But a lot of the light gets lost in these dark gray areas, and it's getting lost to those wavelengths of light are absorbed by water vapor. They're absorbed by carbon dioxide. A little bit is absorbed by oxygen and ozone, methane, nitrogen. At the blue end of the spectrum, Rayleigh scattering is what makes the sky blue. The blue light scatters easily in the atmosphere and looks like it's coming from everywhere, which is why the sky is blue. But this tells me that the light that I'm most likely interested in is in the green range, in the 0.5-ish micron range. And I'll tell you why in a second. When you take a laser and let's say you have a laser pointer and you shine it straight up at the moon, it starts out a couple of millimeters in diameter at the surface of the Earth. By the time that beam gets to the moon, it's probably larger than the moon. That's what happens to coherent light propagating in a vacuum. Depending on the size that the beam starts out with and the wavelength of the light, the beam diverges. It diverges due to diffraction. And diffraction is an edge effect, but a perfect beam will always diverge. And the key is to choose the size of the beam and the wavelength of the beam such that the divergence doesn't hurt you. Okay, so what I did is I put a bunch of graphs together and I said, well, let's start at 0.5 microns of light. Let's assume I've got a 2-meter diameter transmitter and a 2-meter diameter receiver, and look at what happens to the size of the beam as I go from the surface of the Earth up to geosynchronous orbit. And what happens is, if you start at 1 meter radius, the beam blows up to almost 6 meters in radius. And what happens is the power drops off very fast. As a matter of fact, power received by the climber drops 95% by the altitude of geo. And the problem with this curve is it falls off faster than the power required by the climber. So a 2-meter diameter transmitter and receiver is too small. The beam blows up too much and the climber doesn't get enough power to continue its trip. So I said, okay, how about a 5-meter diameter? That's looking much better. The beam goes from 2.5 meters in radius to 3.4 meters in radius. Power drops by about 45%, but there's still over 2 megawatts of power available if you started at 4 megawatts. And the climber doesn't need anything like 2 megawatts of power when it gets to geo. So this is reasonable. And I can tell you what I'd like to do with the light that misses the climber in a second. And then I thought, okay, what happens if I go to a 10-meter diameter receiver and a 10-meter transmitter? Well, the power hardly falls off at all. The beam diverges so little that only 5% of it is lost around the edge of the receiver. This to me seems like too much efficiency. I can afford to throw light away because I don't need that much power at geo, and making a smaller transmitter and a smaller receiver is just overall mechanically easier and cheaper for the climber. It's not even clear that I can lift the 5-meter arrays. I haven't determined that yet, but that's the issue. Can I lift the 5-meter array? So then I said, okay, what if I make the wavelength a little bit longer? 0.84 microns is right in the middle of the range for gallium arsenide photovoltaic cells. And what happens there is at a 5 meter diameter laser transmitter, you start at 2.5 meters in radius and it blows up to 4.6 meters in radius, and the power drops by 70.3% as you move to longer wavelengths. And it makes sense from the equation. If you look at the equation, the wavelength is in the numerator, okay? And the waist is in the denominator. You make the waist smaller, the final radius blows up. You make the wavelength larger, the final radius blows up. So it makes perfect sense. And going with infrared light then in that other window, that window from 1 to 10 microns or whatever it was, that light is too long of a wavelength and the beam blows up too much. So what if you go the other direction? What if you go towards the blue end, 0.3 microns UV laser? Okay, there again, because the wavelength is so short, the power only drops by 22.5%, but that light is much more highly scattered by the atmosphere. So the drop in power going through the atmosphere is higher. So the conclusion about diffraction is that the larger the beam waist at the surface of the Earth, the better you are at not spilling too much light off the edge of the climber. And wavelength in the range of 0.5 microns green light is a very good choice. And as just as a design requirement, going with a smaller diameter laser is cheaper and more feasible. So I'm looking at lasers in the 5-ish meter diameter range. Here's the kicker. The laser light that misses the climber can be collected in geosynchronous orbit at a station in geo, because the lasers from Earth are delivering 80 times the amount of power the sun is delivering. So you can build a smaller photovoltaic array at geo to collect that leftover light than you would build a larger array to collect sunlight. So nothing is wasted here. All right, so atmospheric transmittance. Laser power at sea level is reduced by several phenomena that are all very complicated: turbulence, absorption, and scattering. How can we put a number on the maximum power loss caused by the atmosphere? There is another beautiful curve from the Wikipedia that in the yellow, this is the power delivered to the outside of the atmosphere. So this is the power level of sunlight that reaches the atmosphere as a function of wavelength. 0.5 microns is 500 nanometers. The red curve is the amount of power that makes it to the surface of the Earth. So you take the wavelength, if you know you want 500 nanometers of light, you multiply that by the power that is received in space versus the power received at sea level, you subtract the two, there is almost a 32% drop in power just by pointing a laser straight up out of the atmosphere. And that doesn't take into account clouds. Clouds are much worse. I have an idea on how to possibly deal with clouds by punching holes in them with the lasers, but that's something to be seen in the future. But now I have a number that tells me how much power I lose in the atmosphere. So the next step is, what laser technologies produce green light? And putting multi-megawatt lasers together to make a coherent beam in the megawatt range is something that we have not achieved yet technologically. We think we know how to do it, but the program that the Navy was running for free electron lasers was canceled 10 years ago. They decided they weren't practical to put on ships. So they abandoned the program, but they left a lot of wonderful design technology that's been declassified that I have tried to incorporate in my design. So you could use an argon ion laser. They're very low power. Power efficiency is poor. Copper vapor lasers emit light in the 510 nanometer range. They're a pulsed light source. Erbium doped up conversion lasers, tens of milliwatts of output power, nothing near the range that I need. Dye lasers are tunable and they can be operated in the green spectral region. They're also not that powerful with relatively short lifetimes. Here's a conceptual drawing of a free electron laser, and I'll show you a better drawing in a moment. But the idea is, if you have a beam of electrons from an electron accelerator, and you run it through these alternating north-south magnetic poles, it forces the electrons to wiggle. This is the Wiggler magnet array. When electrons wiggle, they give off light. This light is collected in this optical cavity with a total reflector here and a partial reflector here and an electron dump over here. And a free electron laser can be designed to operate at multiple wavelengths. It is a very high quality beam. It can be throttled so that when you don't need as much power, you just reduce the number of electrons in the accelerator. It's a really ideal situation. Now, that program that I was talking about that the Navy had was a program to put a free electron laser in ships, but the guys who were developing the free electron laser realized they could make it small enough to fit on a 747. So this is a conceptual design where there's an electron linac, there's an optical cavity here, the wiggler is here, and the laser light comes out. Now, they do a little bit of beam expansion here, but we would do a lot of beam expansion. There's a huge difference between the kind of lasers the military is interested in and the kind of lasers that are appropriate for a space elevator climber, because the military wants to concentrate as much power as they can in a small spot to disable an incoming missile. That's not what we're interested in as far as the space elevator is concerned. We don't want to cause atmospheric blooming with the laser light. We want to just deliver electricity from the surface of the Earth to the climber. That's the whole point of the power beaming system. And a wide beam satisfies that. But this design for a nice compact electron linac is great for mounting on the Earth platform that delivers the power to the climber. So now let's look at the third prong of our program. What kind of photovoltaic receiver converts light efficiently back into electricity? Well, the oldest and simplest photocells out there are made of polycrystalline silicon or single crystal silicon. They have efficiencies in the range of 20 to 25%. But as you can see from the graph, here's 500 nanometers. They're not tuned to convert that light very efficiently. They're tuned in this range up here. So that's not the ideal choice. A much better choice is a newer technology that involves semiconductor junctions. Now, the graph shown here is for 3 cells of different materials designed to absorb light in 3 different frequency ranges. I'm not looking to absorb all the possible wavelengths that come in sunlight, for example, but the indium gallium phosphorus subcell, the one down here, has a very nice quantum efficiency for 500 nanometer light. This is the highest power to weight ratio. It's commonly used in aerospace applications. And what I would be talking about is a custom PV array that is only made out of the cells that can absorb the 500 nanometer light. And I could potentially get 30 to 40% efficiency out of such a thing. So we look back at the characteristics, the power characteristics, and compare them to what Edwards talked about in his book. He talked about a number for power density that was about twice what I'm looking at right here. 5.6 megawatts over the square area of the solar collectors. This looks like a very feasible number for photovoltaic arrays. And I'm looking at something like 30 to 40% efficiency on these things. The biggest issue is keeping them cool. They need to be kept cool between 80 degrees C and 100 degrees C to maximize efficiency. The hotter the photocells get, the less they stop converting light into electricity. They lose efficiency. And getting rid of that waste heat is actually a very big problem. So the optimization problem for lasers is we can see that 0.5 micron wavelength light gets out of the atmosphere. It's a good wavelength for that. It might be a little short to get the best efficiency out of PV arrays, but if you design a custom semiconductor mixture, you can do all the conversion that you need. So the laser problem, I think, is solved in that sense. So I then developed a transfer function that to answer the question, how big does the power source have to be on the surface of the Earth? And all of these efficiencies are multiplied together because they pretty much happen in sequence, right? It's a series of things. Power comes in, is lost here. Power comes in, is lost here. And you multiply these things together. And the range of efficiencies, we think we can get a free electron laser as efficient as 33%. That's much higher than they are now. Now they're about 10%. The atmospheric transmittance, when you're near the surface of the Earth, the atmospheric transmittance is 1. You haven't lost power because you're not going through a thick layer of air. Once you get out of the atmosphere, the transmittance goes to 68% because of that layer of air eating up 30-some% of the light. Then the laser power received goes from 1 when the transmitter is close to the receiver. There's no spillover, so the laser all gets absorbed and converted. But it drops down to 55% up at geo because light is now spilling over the side of the photovoltaic array. The photovoltaic efficiency I put in at 40%. Drive electronics, 95%. Motor drive electronics is very efficient. This motor efficiency is an average. When the motor is going slow, its efficiency is terrible. When the motor is going at its rated speed, it's up to 96%. But I put that number in there just as kind of an average. Now, it turns out each one of these efficiencies is actually a function of altitude, except for a couple. So this transfer function needs much more development to be more rigorous. But what it tells us is when the climber is at the surface of the Earth, the system efficiency is about 10%. Okay? And if we need 11 megawatts of power at the surface of the Earth, we need to put 110 megawatts of wall power into the system. You need a naval nuclear reactor to provide this much power. And the platform is probably going to be on out at sea, and you might have a submarine powering it, or possibly even a decommissioned aircraft carrier. I think decommissioned nuclear aircraft carriers are ideal bases for space elevator. If we limit the power to 4 megawatts, basically making the climber start climbing slower, we only need 40 megawatts of input power. Now at GEO, the system efficiency goes down to 3.8%, but the climber needs very little power. So at 28,000 kilometers up, its GEO is 36,000 kilometers up, so most of the way up there, it only needs 0.2 megawatts of power to roll up the ribbon. So 5.3 megawatts at the ground is plenty. So that was the goal, was to determine whether or not the Earth-based power source was practical to lift a 20-ton climber. So then I started thinking to myself, okay, what does it look like? And I drew a very crude platform, and I started putting pairs of laser transmitters, 5-meter laser transmitters, in a circle. I didn't finish the circle, but the first thing that I learned is that if you don't space these 20-ton climbers far enough apart, the lower ones shadow, the PV arrays shadow the upper PV arrays. So that told me something right there about whether or not I could scale up the climber from 20 tons to 200 tons. I believe I have a solution to drive 20-ton climbers. Scaling the space elevator has turned out to be significantly more complicated than that. And I don't have a solution for multi-100-ton climbers, but I can drive 20-ton climbers at least once a day, if not more. So the throughput of the space elevator has to be developed a little bit more for the laser solution. So the conclusion about the laser power is use 0.5 micron light. We need a lot more work to settle on the best laser and PV technologies for a power beaming system. We need a naval nuclear reactor to power the thing at the surface of the Earth. And we can also look at trade-offs between space-based and ground-based lasers, as well as doing solar conversion at the altitudes where the climber doesn't need as much power. All right, here's the takeaway that comes from this study for microwave power. Microwaves have a range of wavelengths from 1 millimeter to 1 meter. The wavelength is so large that the divergence of the beam is far greater than in optical wavelengths. And Avery calculated that the receivers on the climber would have to be over 100 meters in diameter. I have no idea how to support such a monster. So I don't think microwave power beaming either from the surface of the Earth or from space is practical because the receivers on the climber are simply too big. So now for something completely different. We've been studying this lately. What if we used the tether as a wire to feed power up to the climber? And Avery came up with 3 possible ways to use the tether. So what you're looking at here, this gray box is actually looking down at a wheel. And the center line is the axle of the wheel that the motor drives that wheel on. The red and the green are the tether. One of them is at high voltage, one of them is at low or negative voltage. And current passes from one tether to the other to complete the circuit to allow the climber to draw power from the pair of tethers. I didn't have a climber that satisfied this design. This is a new design of climber that I haven't looked at yet. Avery came up with another idea where there is a tether that is not used for traction. It's only used as an electrode, and the other one that the climber rides on is the opposite polarity. The last one is the one where there's a insulating or grounded tether that the climber uses for traction to roll up, but the electrodes are completely free and separate. And the climber that I designed in 2023 can actually satisfy that design. So I started modifying that design to use that concept. And it was based on the buses that I remembered from a kid in Chicago. There used to be an electric bus system where there were these antennae that stuck out from the top of the bus. They used brushes to engage the wires that were suspended above the streets. So that was my inspiration for coming up with this. And here's the thing, though, about putting voltage on the tether. There's something you got to know about the way electric fields distribute around conductors. If you have an oval-shaped conductor, you get this nice electric field, but you can tell the electric field, these field lines get closer together at the end where the radius of curvature of this oval happens. So there is a higher electric field at the ends here than on these long flat surfaces, and that's where you expect breakdown. And you can see in this shape where the radius of curvature gets very small, the field intensity gets very high. This kind of electrode is very likely to cause breakdown because the electric field gets so high that it tears the air molecules apart and it begins to cause arcs. Okay? This effect would be incredibly magnified on the edges of a flat ribbon that is as thick as a sheet of paper. The electric field would simply be enormous on the edge of that ribbon. So instead, I said, what if I made graphene electrodes that were cylindrical? And I separated them an appropriate distance. And the electric field, then you can tell around 2 circular electrodes is much more distributed and doesn't have a concentration like it has when there's a sharp point in the system. Avery developed this SPICE model. These are climbers. Here's one of the tethers. Here is the other electrodes, rather. Here's the other electrode. Each one of these crossing points are climbers, and there are 7 of them. And what Avery figured out is if he put 500,000 volts on the electrodes at the surface of the Earth and 500,000 volts from a power supply at GEO, the tether has enough electrical conductivity that it doesn't waste too much power. It only loses a certain percentage, a small percentage of power to the Joule heating of the tether from not being a superconductor. So this is a conceptual model. You've got a power supply at the Earth port. You've got a 500 kilovolt converter here, and you've got 7 climbers. The trip takes about a week. You launch a climber every day. So there's at one time there are 7 climbers on the tether, and then there's a 500 kilovolt converter and some solar power at Geo that only has to put out about 3.2 megawatts of power, where the Earth port has to put out over 10.6 megawatts of power to drive these climbers. And each climber draws as much power as it needs by changing its own resistivity. So using the 2023 model of the climber, I just put these electrodes on opposite sides, and I discovered that this volume is available for a DC converter to go from the 500 kilovolts to the 800 volts that the climber needs. We don't know if that kind of DC converter can be fit in this volume. That's one of the open questions. These are the arms that go out to brushes that brush along these graphene electrodes. But here's the problem with this design. So you can see a close-up of the converter. The problem is if you take the climber away, the electrodes and the mechanical tether are not coupled to each other. And they're not coupled to each other because the climber has to surround the tether. It has to go all the way around the tether to be able to squeeze the wheels against the tether. So this is a non-starter because these 3 separate tethers have totally different dynamics, and they're 8 meters apart. So I said, okay, what's another way to do this? And I said, what if I move the electrodes and attach them to the tether so that the 500,000 volts actually runs through the center of the climber? We don't actually know if this works because we haven't looked at the electrostatics of the climber. We haven't looked at can the climber not break down to that kind of voltage going through the center of it. The advantage of this design is that the tether, which is now insulating, separates the 2 electrodes and it becomes a mechanically stable system. Okay. And I just took I got rid of the arms and I took the brushes and moved them over to the space where the converters were and put them on the sides of the tether to be able to draw power to both halves of the climber. Unfortunately, this object here in the red box is what a very large megavolt DC converter for Earth use looks like. This is the thing that we don't know can be made small enough to fit on a climber to do the reverse conversion from the 500 kilovolts down to 800 volts. We simply have to put more work into this. But the systems that are on Earth need these kind of large, rounded surfaces to keep the electric fields low enough that you don't have lightning going through these things. So we have 2 concerns. One concern is when the tether goes through the ionosphere, the air is basically conductive, and it causes a leakage current between the electrodes. The other concern is high voltage breakdown between the 2 tethers. And from Avery's work, it looks like number 1 is a bigger concern. Avery calculated the resistance of the volume of air around the tether, and where he was hoping to get a mega ohm, he got 3.7 ohms. This is too low. We would lose hundreds of kiloamps of leakage current into the ionosphere around the tether. That's a non-starter. And he said to get the resistance between the 2 electrodes up into the mega ohm range, you have to separate them by 300 kilometers. That's not a practical separation for a climber. Climbers can't be 300 kilometers wide. So this idea doesn't work going through the ionosphere, but it works going up just below the ionosphere. And you don't need a power supply that close to the surface of the Earth. Like, for example, in the previous block diagram I showed you, there was a power supply at the surface of the Earth. There was a power supply at Geo. If you're only using the tether as a conductive wire up to the point of the ionosphere, you only need the power supply at the surface of the Earth. What takes over driving the climber out of the atmosphere then and up to Geo? It would have to be lasers. It would have to be something else. because you can't make it work going through the ionosphere. I'm not sure if putting a larger power supply at GEO does the trick. We haven't discussed that actually. Actually having a break for the ionosphere, having electric conductivity below and electrical conductivity above, and then some mechanism to get through the ionosphere. It's 150 kilometers of altitude. But that's something we need to talk about. All right, discharging the tether. This is a really complicated process, and the altitude is constantly changing the discharge voltage because the density of air changes. And there's something called a Paschen curve that shows you that perfect vacuum gives you one answer, and 1 atmosphere of pressure at the surface of the Earth gives you a different answer, and it goes through a curve when you get into the low altitude, the low atmospheric pressure regions at high altitude. So 1 meter of separation may be the minimum to avoid electric discharges, but it doesn't solve that problem of the leakage current. So conclusions about the conductive tether. We've shown a version that works up to a certain point, but has problems in the atmosphere, in the ionosphere. It uses DC because DC is easy to get off the electrode with a brush. You could do it inductively if instead of powering the tether with DC electricity, you put AC electricity on it, alternating current electricity, but that turns the tether into an antenna. And it becomes a much more complicated problem, and you begin to radiate the power out into the solar system from your giant space elevator antenna. So that's a problem with using AC power on the tether. So there's clearly issues that we have to figure out. And this is a bunch of references, and the rest is backup. So I'm basically done. I've showed you 2 different methods. I think the free electron laser photovoltaic arrangement for 20-ton climbers is a perfectly feasible and workable solution. We don't know how to scale it up yet. So I am happy to take questions. I hope I didn't go too fast or.
I see one person. Why don't you stop sharing, Larry? And I see one person has their hand raised. Maybe let's see if we can take a look at that and let them ask a question. Okay, let me just see. I want to allow Aiden, I'm going to allow you to talk and ask your question. So you have to make sure you're unmuted.
Thank you. Why not use mirrors in orbit to deflect light? Sorry, why not use mirrors in orbit to deflect light into solar panels which are on board a climber? Thank you.
So, Aiden, the thing is, the diffraction effect would be so large that, I mean, that is a possible thing that is a trade space that we need to finish looking at. But there is a very strong reason to put the power supply near the surface of the Earth, because that's where the power is needed. And if you put the power supply up in space, it has to be much bigger to account for the losses of getting through the atmosphere. The other big problem with all power supplies is heat dissipation. And on Earth, we have water. We have convection, conduction, and radiation to dissipate heat. In space, all you have is thermal radiation, and it's a very inefficient process. So power supplies to deliver megawatts of power in space are a really big deal.
Aiden, did that answer your question?
Yes, thank you.
Great. I see another hand is raised. Timothy, I'll let you ask a question. Make sure you're unmuted.
Can you hear me?
Yep.
Yes. Timothy, go ahead.
Timothy seems to have disappeared off the Zoom.
Oh. That is strange. Okay. Timothy, you still there? I saw Carl had his hand raised as well. Let's see. Let's give him a chance. Yep, I don't see them there anymore. There we go. Well, let's get a few other things in while a few other people, feel free if you want to raise your hand to ask a question. And we did have a lot of questions beforehand. But Larry, great presentation. Is it possible to give everybody who's not familiar with the entire concept of space elevators kind of a space elevator 101 intro real fast to just explain? Because I saw a couple of things about what the tether is, what the climber is. So maybe you might be able to just describe it real briefly.
So a space elevator in basic is an Earth-based platform with a cable that is 100,000 kilometers long, that's terminated in a counterweight at 100,000 kilometers, and the center of mass of the entire system is just above geosynchronous orbit. So the tether, which is a material like graphene, is always in tension throughout the length of the cable. And the idea is because the Earth is spinning fast enough that we have a nice altitude for geosynchronous orbit, you can climb from the surface of the Earth up this cable to be in geo. And the Coriolis force that the simple act of climbing up the tether makes you be fast enough to be at geo-orbital speed. So you're actually stealing a little bit of the angular momentum of the Earth every time you climb a tether.
Interesting. Yes. And I didn't realize you were talking about that at least the 20-ton climbers you describe in your examples. So it'd take about a week to get there.
Takes about a week. Yeah.
Okay.
We want to explore the design space to make it faster, but there are a number of mechanical limitations to, I mean, you look at the fastest electric vehicle on Earth and it's only 500 kilometers per hour. And that's a vehicle that drives once, right? These things have to be very reliable. They have to be able to make the trip all the way from the surface of the Earth, possibly out to the apex at 100,000 kilometers. No gas stations, no repair stations on the way. So yeah, it's a big deal making them go fast.
Interesting. How do you account for that kind of reliability? I mean, you know, we it sounds very challenging.
So I built a number of features into the climber, such as a motor operated latching system that connects the two halves of the climber to each other, so that in the event of an emergency, the climbers can uncouple and fall away from the tether. They would have to have a miniature thruster system to make sure they didn't hit the Earth port, but they could be pushed far enough away from the tether to fall through the atmosphere and just land in the ocean if they were blocking traffic, for example.
Right. Okay, interesting. Let me see a few of the other questions that have come in. I see Carl has asked quite a few questions in the Q&A function. Let's you know, in terms of something like this, is this a commercial effort or would it be a government enterprise or kind of a combination?
It's expensive enough that it's probably multiple governments. And it's multiple governments because, first of all, we're talking about making a transportation infrastructure. We would like the space elevator system to be located on the equator at multiple points around the equator, with 6 or more space elevator tethers taking traffic up every day, and be a transportation infrastructure for the entire world. And I know there were questions in the number of questions you sent me before where people were asking about, well, how do you defend this thing against terrorist attacks? That's an issue, right? You know, if someone tries to fly an airplane into it. Now, it's possible that if someone does try and fly an airplane into it, it could inflict as much damage on the airplane. I mean, literally, if you fly from the side, it may be possible that the graphene tether slices the airplane.
Okay.
Just to use one example,
Right.
but we haven't worked out all the dynamics of that.
Right. You've obviously done a tremendous amount of work. What is actually happening out there on the space elevator concepts to get us to something functional?
So the Japanese have a very strong space elevator program. Obayashi Corporation every few years puts out the same old stuff if you ask me. They put out some very glitzy stuff back in 2014, which they really have not developed since then. And a person like me who's familiar with some of the problems of the space elevator just looks at it and says, well, they didn't think about this, they didn't think about this, they didn't think about this. But there are a number of governments and companies thinking about this. Space Railways is one that is going to release its technology sometime next year. I know the president of that company, and I am dying to find out how he claims he's solved problems that I've presented here about scaling up the size of the climber. And I don't know how he's done it. One possibility is he just didn't do all the calculations he needed. I don't know. I don't know if he's got something that can take multiple hundreds of tons up very fast. How did I miss it? I just don't know.
Maybe
It's making me crazy.
Right. In terms of powering it, you mentioned using a naval nuclear reactor. What's the actual feasibility of getting something like that?
The French sell them. The French
really?
sell
Okay.
submarines. Yeah,
Right.
and I think when aircraft carriers are decommissioned by our Navy, I bet it's possible, especially if the government were involved, one of the governments involved in building the infrastructure. I bet they would contribute such things.
Right. Well, I know there was a lot of challenges when they decommissioned the Enterprise and its nuclear reactors, because they're basically built into the hull.
Right.
You'd have to cut everything out.
So that's an argument where you might want something a little more modular.
In terms of, I saw a couple questions in terms of cost. Do you see this as being, in terms of the power needed to generate to get these climbers into space versus how much energy is going to need to be produced? Do you see is it feasible from a financial standpoint?
So this is a really good question. When you're in the rocket world, you're always talking about dollars per kilogram to get stuff into orbit. We would like to move away from that paradigm, because when you are talking about railroad systems and highway systems, you're not talking about dollars per kilogram of traffic on those things, right? Those things have a large functionality, and you have a different set of questions to be asked about that. So the first elevator 20 years ago, Brad Edwards estimated the first elevator could be built for $10 billion. That number is ridiculously low, in my opinion.
10 billion?
Today, it's ridiculously low.
Okay.
The more I study this thing, the more technologies I realize need to be developed. Climbers are on the really hairy edge. When I first started designing climbers, I was doing them out of aluminum, because I'm very familiar with mechanical design using aluminum. Aluminum turns out to be too heavy. The structure of the climber became too heavy just because it was made out of aluminum. It's now, the climbers have to become more expensive because they're made out of carbon fiber reinforced polymer.
Right.
But they're a lot stronger and lighter, so they make it possible to climb.
Interesting. I saw there were a couple questions about this seems like a great system to have either on the moon, and then I see a question from Richard Anderson about he's writing a sci-fi novel where they're building a space ladder on Mars. The anchor base is near the equatorial Planet Mons. Problems are much easier in that place.
Yes. And there have been a couple of space elevator stories that take place on Mars, like Kim Stanley Robinson's books. Right, Mars, because of its lower gravity, you don't need as strong a material. The moon is a different problem. The moon is not spinning fast enough to make the kind of space elevator you would make on the Earth. The moon's space elevator basically dangles from the near side of the moon and is gravity stabilized, getting towards the L2 or L1 point. I forget which one is on the near side. Maybe L2 is on the far side and L1's on the near side. But anyway, it's a totally different space elevator concept. It's really like climbing a ladder to the moon, because it's just gravity stabilized.
Right. Interesting. I see a Tim Cash who had raised his hands. He has a comment there in the chat. Let me just get to that. I think you'll find that interesting there. Let's see if I can get to it here.
He's a cable design engineer.
Yes, yeah, he's a cable design engineer and sees actually applications, irrespective of the space elevator. Well, that's an interesting observation.
Yeah, well, I mean, if once we get the production capability, so people ask in the questions that you sent to me beforehand, a number of people asked, how soon can we see a space elevator?
Yes, I was going to ask that eventually.
The problem why we don't have a space elevator right now is because we don't know how to make the material. That there are 3 candidate materials that we think are strong enough. You need a material that's about 100 times stronger than steel to be able to support itself over that entire length and not be so heavy that you can't lift it off to get it up there. So graphene, single crystal graphene or polycrystalline graphene sheet is a possibility. Carbon nanotubes are still in the running, and boron nitride, hexagonal boron nitride. We have not been able to figure out any of these materials in bulk, in the kind of quantity that you need to make a tether material, ribbon material. Once we do, like Arthur Clarke said, the space elevator will be built the day after people stop laughing at the idea.
Okay, right. How is the tether? How would the tether be assembled? I'm just, I know when you're building a building, they slowly move a crane up to lift the materials. How is this tether extended 100,000 kilometers?
So Edwards worked out a deployment scenario that's outlined in the book. And it works for carbon nanotubes if you had long enough carbon nanotubes.
Yeah.
What's that?
I'll have to get that book.
It's a great book. It's still relevant. 20 years later, and it's still relevant. The deployment scenario changes depending on the material. And so one concept is you boost small reels of material into low Earth orbit. You already have to build the lasers to power the elevator, so you can use the lasers to power those spacecraft in LEO up to GEO, right? So there can be MHD spacecraft that are using the laser light, and so once the reel of material gets to GEO, you can begin to unreel it, and half of it goes out towards the apex, and the other half goes down towards the surface of the Earth. And you have to catch it when it gets down through the atmosphere and anchor it on the Earth platform. And we are developing, the International Space Elevator Consortium is developing a simulator to simulate all of the dynamics that are going to happen to the elevator. And deployment turns out to be difficult. I mean, it puts a lot of stress on the tether in that last few minutes, literally, of bringing it down through the atmosphere and connecting it to the base. So if you haven't broken it in the deployment, it's probably going to be okay.
Well, I'm definitely going to pick up that book. Can you tell us a little bit about the ISEC, about what you do and the role you play?
So ISEC is an all-volunteer organization. We have, I think, something like 100 members, dues-paying members. We have a conference every year, and we go to NSS. We always have a space elevator track at ISTC, and we sponsor studies. We volunteer ourselves and our time to develop ideas about the space elevator. I was involved from 2020 to 23 developing a very detailed engineering study of the interface between the climber and the tether, and we learned some really interesting things about both climbers and multi-layer graphene. Multi-layer graphene is very strong in tension, but it probably is not strong enough in shear. So if you have wheels that are trying to grip the outer layer, they may not be gripping anything other than the outer layer, because the outer layer is shearing with respect to the inner layers. So we're working on ways to increase the shear strength of graphene sheet.
Interesting. I see Aiden has his hand up again. Aiden, did you want to ask another question? Don't hear anything. Let me check. Let me just make sure here.
Hello.
Oh, there
What
you
your
are.
thoughts on the morphing wing technology, and can it be applied to space elevators? Thank you.
I don't know what morphing wing technology is. What is that? Have you
Aiden,
heard that, Bert?
I've not heard that. No, Aiden,
It's just something you can do with a wing to help increase airflow above the wing rather than below to help create lift.
oh, that's what you mean. Okay.
Since we're not actually flying, we're not using the atmosphere for
Yeah.
lift. I'm not sure how that would help. There might be ways to reduce the drag on the climber or on the PV arrays. That would be very helpful. If I could figure out how to reduce the drag on those things, that would be terrific.
Right. Larry, how did you get interested in space elevators?
Back in 2004, there was a lull in some of my contracts. Federal government was having a rough time back then, and I just happened to find this book. This book is what got me into it. I read the book and I thought, this is an electric vehicle. I'm a mechanical engineer. I ought to be able to design an electric vehicle that can roll up this ribbon into space. And that's what I've been doing for the last 20 years.
Interesting. Do you see a connection between what you do professionally and your interest in space elevators?
So one of the experiments I worked on over the years was called the neutron electric dipole moment experiment. And we had to develop a non-metallic cryostat. So I learned a lot about working with carbon fiber composites, which was directly related to converting the climbers from an aluminum skeletal structure to a CFRP skeletal structure. So yeah, there's definitely feedback. And I learned so much. I mean, I had to remember the starred chapters in your mechanics classes, the things you didn't cover in class.
Sure. Yes.
I've had to go back and read some of those.
Okay. You still have all those textbooks?
Absolutely. I've got a whole room full of them.
Me too. Okay. I see Larry Ahern has his hand up to ask a question. Larry? Larry, you're on mute.
Can you hear me now?
Now we hear you. Yep.
Okay. It's not so much a question as an observation. You're not going to be able to use space elevators for people because the biggest problem is these people when they arrive in geosync, they're going to be insane because of eight days of elevator music.
Larry, you're absolutely right, and it's a good point. The space elevator as conceived right now is a cargo elevator, and the main reason is because most of its trip is through the Van Allen radiation belts. And with a 20-ton climber, there simply isn't enough mass to protect human beings unless they're in cryostasis where they won't go insane from the elevator music. But Space Railways is planning on having commuter service. I don't know how they're going to do it. That's another one of the many questions I have for that company.
Right.
8 days, you're gonna the bathrooms, the sleeping quarters, and everything else. It's going to be like a cruise ship.
And you can see the size of a cruise ship, right? I actually have a talk that I gave at last year's ISEC conference about how do you scale up from a 20-ton to a 200-ton climber. A 200-ton climber is not even as big as a 747, and you wouldn't want to spend a week on a 747.
No, not at all.
Yes. Yeah. Okay.
Let's see. Let me see if the other questions here that I can go through. Well, I guess this is just tying into what Larry just mentioned. Carl asked if this could be used for space tourism, but there certainly are limitations to it. I mean, they're talking about balloons to take people up to about 100,000 feet, but
so we have talked about how do you have platforms at different altitudes. Like, for example, you could have a platform where the elevation was high enough that you were experiencing the gravity of Mars or the gravity of the moon, and you could do studies there about long-term living at those gravities and what its effect on biology is. What that requires is another set of tethers, independent tethers, massive tethers to support structures at those altitudes. It's from an engineering sense, it's feasible, it's possible. It's very financially challenging and very technically challenging in the sense that the tethers required to support these structures are very large.
Right. That's a kind of a follow-on question that someone submitted about the environmental impact of a space elevator. Have you looked at that?
Okay, what I can tell you is that driving climbers up the tether by nuclear power and using electricity doesn't have anywhere near the environmental impact of starships and rockets in general. I think one of the big problems with rocket plumes is the fact that a lot of the output stays in the upper atmosphere, which I think is somewhat problematic. We're not talking about any carbon emissions using a nuclear reactor or using some of the other options that we're talking about. I mean, I've always thought reactors were the ultimate green technology.
Oh, yes. Yep. Let's see. I think I see another message in here. Just want to make sure I get everything as I can. And let's see. What role can universities, startups, and the general public play in accepting the research and development related to space elevators? Because as you said, you passed that, that initial reaction to it, right?
The Giggle test.
Yes.
So certainly material science is something that universities are actively engaged in. What we have experienced, which is kind of odd, some companies that we've talked to that make graphene and have particular niche uses for small particles of graphene, like in electronics or like in additives to concrete or something like that, have simply never thought about making the strongest fabric in the world. They've never thought about making macroscopic quantities of it. And we have to open their minds to that possibility to develop the technology. And anybody who develops that technology is going to improve sports equipment, military hardware. There are so many earthly uses for the strongest fabric in the world.
Right.
Actually, that's one of the ways that we talk about paying for the space elevator is during the material development process, spinning off companies whose profit goes into developing elevator material.
Let's see. I'm looking at some of the other questions that were submitted here, and one of them talks about the potential of satellites hitting the space elevators. But
satellites and orbital debris are
yes.
Those are two big deals. And I'm very glad that there are a number of companies starting up who are looking at how to reduce the amount of orbital debris, because orbital debris is a problem for everyone. We don't want a Kessler event. So let's pretend that we live in a world where we have pulled all the junk out of low Earth orbit. We've deorbited that stuff. The lasers that I'm talking about, there's actually a patent by one of the guys who worked on the free electron laser project for using those kinds of lasers to deorbit orbital junk, orbital debris, by the ablation process. You heat up the surface and the materials can just fall into the atmosphere and burn up. If we got rid of all the junk, the bolts, the paint chips, and all the other stuff, the boosters or whatever, there would still be constellations of Starlink satellites and all the other low Earth orbit satellites. When there were far fewer than 40,000 Starlink satellites, we thought that we could simply drive the base of the Earth port back and forth in the ocean and induce a transverse wave in the elevator that would allow them to pass the satellites. I don't think we have done that analysis for the dynamics of 40,000 or more satellite constellations. So that's a big deal. And to me, that becomes a political problem, because my in-laws live in Upper Michigan, where the only option for high-speed internet for them is Starlink. They don't need a space elevator. They need high-speed internet.
Right.
Okay. So that's the political problem. once we have the technology to build a space elevator, the next thing we have to figure out is how do we satisfy everybody in rural areas with high-speed internet,
Right.
so that we don't need constellations cluttering up low Earth orbit.
Very true. I see we're about 5 minutes past our usual end time. I'd like to get two last quick questions in, Larry, if it's okay with you.
Sure.
Do you, as a space elevator advocate, maybe look at yourself as in the early days of rocketry advocates, right? They weren't, people said, what are you guys doing? Come on, it's never going to happen. We're never going to get rockets into space. And do you kind of feel like you're maybe like them?
We might actually be as far back as Wilbur and Orville.
Very true. Okay. And I did see a funny note from Carl in the Q&A. He said, well, once you get to the top of one of these beanstalks, what will we see? I'd like to.
I haven't been to the restaurant in Disney World that is supposed to look like a space elevator. I don't know how accurately it simulates that, but clearly from GEO you see a fabulous view of the Earth. From the apex anchor it would be much smaller, even because you're 100,000 kilometers away.
Very good. I like that. Well, sounds good. Thank you so much, Larry. That was really, really interesting. And I think we had a great discussion around it. And I think we'll be hearing more about space elevators. And if everyone is interested, as Larry said, there is a space elevator track typically at the ISDC. And the next ISDC will be in Orlando in June.
I'll be there.
15th to 20, and Larry will be there, so you get a chance to meet him. And hear more about space elevators. So again, thank you so much, Larry. That was great. Really appreciate it. What I'm going to do now is share my screen, everybody, one last time.
Bert, if I could make one last statement.
Absolutely. Feel free.
If anybody out there has a technical background and some free time and wants to not get paid but think really hard about this problem, by all means, please contact me.
Absolutely. Yes, I love that. So what you're saying is the hours will be long, but the pay stinks.
Exactly.
But there's a lot of satisfaction. Oh, very good. Thank you so much, Larry. As always, everybody, again, thank you for joining us. I do want to thank my two NSS colleagues here, my colleague Larry Ahern, VP of Chapters, and my colleague Fred Becker, who handles the technical aspects and has worked to actually do this live stream on YouTube. So hopefully that is going pretty well. And so thank you both for that. I'm going to share my screen one last time, everybody, as we close out for the evening. Okay. There we go. And let me just get this up there. Okay. So everybody, thank you again for joining us. I know it's been a few weeks since the last Space Forum. We really appreciate you taking the time out of your evenings or mornings to join us. We hope to see you next week where we will have the presentation on Via Space. Again, a great startup here on the Space Coast, and a young engineer, Josh Zugan, who's going to be telling us all about what they're doing, creating these hybrid rockets. So I think you'll find that fascinating. So look for the invite early next week. Again, I want to thank my colleagues. Thank you all for attending. If you are in today's time zone, have a great evening. If you're in tomorrow's time zone, have a great day. And of course, have a great weekend.